Part 2, Chapter 11 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Aaron Carlo in San Clemente, California. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 2, Chapter 11, Part 1. Recent Comets. Continued. The mystery of comets' tails had been to some extent penetrated. So far, at least, that by making certain assumptions strongly recommended by the facts of the case, their forms can be, with very approximate precision, calculated beforehand. We have, then, the assurance that these extraordinary appendages are composed of no ethereal or supersensual stuff, but of matter such as we know it, and subject to the ordinary laws of motion, though in a state of extreme tenuity. Olbers, as already stated, originated in 1812 the view that the tails of comets are made up of particles subject to a force of electrical repulsion proceeding from the sun. It was developed and enforced by Bessel's discussion of the appearances presented by Halley's comet in 1835. He, moreover, provided a formula for computing the movement of a particle under the influence of a repulsive force of any given intensity, and thus laid firmly the foundation of a mathematical theory of cometary emanations. Professor W. A. Norton, of Yale College, considerably improved this by inquiries begun in 1844, and resumed on the apparition of Donati's comet, and Dr. C. F. Pape at Altona gave numerical values of the impulses outward from the sun, which must have actuated the materials respectively of the curved and straight tails adorning the same beautiful and surprising object. The physical theory of repulsion, however, was, it might be said, still in the air. Nor did it even begin to assume consistency until Zollner took it in hand in 1871. It is perfectly well ascertained that the energy of the push or pull produced by electricity depends, other things being the same, upon the surface of the body acted on, that of gravity upon its mass. The efficacy of solar electrical repulsion relatively to solar gravitational attraction grows, consequently, as the size of the particle diminishes. Make this small enough, and it will virtually cease to gravitate, and will unconditionally obey the impulse to recession. This principle Zollner was the first to realize in its application to comets. It gives the key to their constitution. Admitting that the sun and they are similarly electrified, their more substantially aggregated parts will still follow the solicitation of his gravity, while the finely divided particles escaping from them will, simply by reason of their minuteness, fall under the sway of his repellent electric power. They will, in other words, form tails. Nor is any extravagant assumption called for as to the intensity of the electrical charge concerned in producing these effects. Zollner, in fact, showed that it need not be higher than that attributed by the best authorities to the terrestrial surface. 40 years have elapsed since M. Brédikhine, director successively of the Moscow and the Pulkovo observatories, turned his attention to these curious phenomena. His persistent inquiries on the subject, however, date from the appearance of Coggia's comet in 1874. On computing the value of the repulsive force exerted in the formation of its tail, and comparing it with the values of the same force arrived at by him in 1862 for some other conspicuous comets, it struck him that the numbers representing them fell into 3 well-defined classes. This idea was confirmed on further investigation. In 1882, the appendages of 36 well-observed comets had been reconstructed theoretically, without a single exception being met with to the rule of the 3 types. A further study of 40 comets led, in 1885, only to a modification of the numerical results previously arrived at. In the first of these, the repellent energy of the sun is 14 times stronger than his attractive energy. The particles forming the enormously long straight rays projected outward from this kind of comet leave the nucleus with a mean velocity of just 7 kilometers per second, which, becoming constantly accelerated, carries them in a few days to the limit of visibility. The great comets of 1811, 1843, and 1861, that of 1744, so far as its principal tail was concerned, and Halley's comet at its various apparitions, belonged to this class. Less narrow limits were assigned to the values of the repulsive force employed to produce the second type. For the axis of the tail, it exceeds by 1/10 the power of solar gravity. For the anterior edge, it is more than twice; for the posterior, only half as strong. The corresponding initial velocity, for the axis, is 1,500 meters a second, and the resulting appendage, a scimitar-like or plumy tail, such as Donati's and Coggia's comets furnished splendid examples of. Tails of the third type are constructed with forces of repulsion from the sun ranging from 1/10 to 3/10 that of his gravity, producing an accelerated movement of attenuated matter from the nucleus, beginning at the leisurely rate of 300 to 600 meters a second. They are short, strongly bent, brush-like emanations, and in bright comets seem to be only found in combination with tails of the higher classes. Multiple tails, indeed, that is, tails of different types emitted simultaneously by one comet, are perceived, as experience advances and observation becomes closer, to be rather the rule than the exception. Now, what is the meaning of these three types? Is any translation of them into physical fact possible? To this question, Brédikhine supplied, in 1879, a plausible answer. It was already a current surmise that multiple tails are composed of different kinds of matter, differently acted on by the sun. Both Olbers and Bessel had suggested this explanation of the straight and curved emanations from the comet of 1807. Norton had applied it to the faint light tracks proceeding from that of Donati, Winicke to the varying deviations of its more brilliant plumage. Brédikhine defined and ratified the conjecture. He undertook to determine, provisionally as yet, the several kinds of matter appropriated severally to the three classes of tails. These he found to be hydrogen for the first, hydrocarbons for the second, and iron for the third. The ground for this apportionment is that the atomic weights of these substances bear to each other the same inverse proportion as the repulsive forces employed in producing the appendages they are supposed to form, and Zollner had pointed out in 1875 that the heliofugal power by which comets' tails are developed would, in fact, be effective just in that ratio. Hydrogen, as the lightest known element, that is, the least under the influence of gravity, was naturally selected as that which yielded most readily to the counter-persuasions of electricity. Hydrocarbons had been shown by the spectroscope to be present in comets, and were fitted by their specific weight, as compared with that of hydrogen, to form tails of the second type, while the atoms of iron were just heavy enough to compose those of the third, and, from the plentifulness of their presence in meteorites, might be presumed to enter in no inconsiderable proportion into the mass of comets. These three substances, however, were by no means supposed to be the sole constituents of the appendages in question. On the contrary, the great breadth of what, for the present, were taken to be characteristically iron tails were attributed to the presence of many kinds of matter of high and slightly different specific weights, while the expanded plume of Donati was shown to be, in reality, a whole system of tails made up of many substances, each spreading into a separate hollow cone, more or less deviating from, and partially superposed upon the others. Yet these felicities of explanation must not make us forget that the chemical composition attributed to the first type of cometary trains has, so far, received no countenance from the spectroscope. The emission lines of free incandescent hydrogen have never been derived from any part of these bodies. Dissentient opinions, accordingly, were expressed as to the cause of their structural peculiarities. Ranyard, Zenker, and others advocated the agency of heat repulsion in producing them. Kerr somewhat obscurely explains them through the evolution of gases by colliding particles. Hertz of Vienna concludes tails to be more illusory appendages produced by electrical discharges through the rare medium assumed to fill space. But Hearn conclusively showed that no such medium could possibly exist without promptly bringing ruin upon our daedal Earth and its revolving companions. On the whole, modern researches tend to render superfluous the chemical diversities postulated by Brédikhine. Electricity alone seems competent to produce the varieties of cometary emanation they were designed to account for. The distinction of types rests on a solid basis of fact, but probably depends upon differences rather in the mode of action than in the kind of substance acted upon. Suggestive sketches of electrical and light pressure theories of comets have been published respectively by Mr. Fessenden of Allegheny and by M. Arrhenius at Stockholm. Although evidently of a tentative character, they possess great interest. Brédikhine's hypothesis was promptly and profusely illustrated. Within 3 years of its promulgation, 5 bright comets made their appearance, each presenting some distinctly peculiarity by which knowledge of these curious objects was materially helped forward. The first of these is remembered as the Great Southern Comet. It was never visible in these latitudes, but made a short though stately progress through southern skies. Its earliest detection was at Cordoba on the last evening of January 1880, and it was seen on February 1st as a luminous streak extending just after sunset from the southwest horizon towards the pole, in New South Wales, at Montevideo, and the Cape of Good Hope. The head was lost in the solar rays until February 4th, when Dr. Gould, then director of the National Observatory of the Argentine Republic at Cordoba, caught a glimpse of it very low in the west, and on the following evening Mr. Eddy at Grahamstown discovered a faint nucleus of a straw-colored tinge about the size of the annular nebula in Lyra. Its condensation, however, was very imperfect, and the whole apparition showed an exceedingly filmy texture. The tail was enormously long. On February 5th it extended, large perspective retrenchment notwithstanding, over an arc of 50 degrees, but its brightness nowhere exceeded that of the Milky Way in Taurus. There was little curvature perceptible. The edges of the appendage ran parallel, forming a nebulous causeway from star to star, and the comparison to an auroral beam was appropriately used. The aspect of the famous comet of 1843 was forcibly recalled to the memory of Mr. Janisch, governor of St. Helena, and the resemblance proved not merely superficial. But the comet of 1880 was less brilliant, and even more evanescent. After only 8 days of visibility, it had faded so much as no longer to strike, though still discoverable by the unaided eye, and on February 20th it was invisible with the great Cordoba equatorial pointed to its known place. But the most astonishing circumstance connected with this body is the identity of its path with that of its predecessor in 1843. This is undeniable. Dr. Gould, Mr. Hind, and Dr. Copeland each computed a separate set of elements from the first rough observations, and each was struck with an agreement between the two orbits so close as to render them virtually indistinguishable. "Can it be possible," Mr. Hind wrote to Sir George Airy, "that there is such a comet in the system, almost grazing the sun's surface in perihelion, and revolving in less than 37 years? I confess I feel a difficulty in admitting it, notwithstanding the above extraordinary resemblance of orbits." Mr. Hind's difficulty was shared by other astronomers. It would, indeed, be a violation of common sense to suppose that a celestial visitant so striking in appearance had been for centuries back an unnoticed frequenter of our skies. Various expedients, accordingly, were resorted to for getting rid of the anomaly. The most promising at first sight was that of the resisting medium. It was hard to believe that a body, largely vaporous, shooting past the sun at a distance of less than 100,000 miles from his surface, should have escaped powerful retardation. It must have passed through the very midst of the corona. It might easily have had an actual encounter with a prominence. Escape from such proximity might, indeed, very well have been judged beforehand to be impossible. Even admitting no other kind of opposition than that dubiously supposed to have affected Encke's comet, the result in shortening the period ought to be of the most marked kind. It was proved by Oppolzer that if the comet of 1843 had entered our system from stellar space with parabolic velocity, it would, by the action of a medium such as Encke postulated, varying in density inversely as the square of the distance from the sun, have been brought down by its first perihelion passage to elliptic movement in a period of 24 years, with such rapid diminution that its next return would be in about 10. But such restricted observations as were available on either occasion of its visibility gave no sign of such a rapid progress towards engulfment. Another form of the theory was advocated by Klinkerfues. He supposed that 4 returns of the same body had been witnessed within historical memory, the first in 371 B.C., the next in 1668, besides those of 1843 and 1880, an original period of 2039 years being successively reduced by the withdrawal, at each perihelion passage, of 1/1320th of the velocity acquired by falling from the far extremity of its orbit towards the sun, to 175 and 37 years. A continuance of the process would bring the comet of 1880 back in 1897. Unfortunately, the earliest of these apparitions cannot be identified with the recent ones, unless by doing violence to the plain meaning of Aristotle's words in describing it. He states that the comet was first seen during the frosts and in the clear skies of winter, setting due west nearly at the same time as the sun. This implies some considerable north latitude, but the objects lately observed had practically no north latitude. They accomplished their entire course above the ecliptic in 2 hours and a quarter, during which space they were barely separated a hand's breadth, one might say, from the sun's surface. For the purposes of the desired assimilation, Aristotle's comet should have appeared in March. It is not credible, however, that even a native of Thrace should have termed March winter. With the comet of 1668, the case seemed more dubious. The circumstances of its appearance are barely reconcilable with the identity attributed to it, although too vaguely known to render certainty one way or the other attainable. It might, however, be expected that recent observations would at least decide the questions whether the comet of 1843 could have returned in less than 37, and whether the comet of 1880 was to be looked for at the end of 17½ years. But the truth is that both of these objects were observed over so small an arc, 8 degrees and 3 degrees respectively, that their periods remained virtually undetermined. For while the shape and position of their orbits could be and were fixed with a very close approach to accuracy, the length of those orbits might vary enormously without any very sensible difference being produced in the small part of the curves traced out near the sun. Dr. Wilhelm Meyer, however, arrived by an elaborate discussion at a period of 37 years for the comet of 1880, while the observations of 1843 were admittedly best fitted by Hubbard's ellipse of 533 years. But these Dr. Meyer supposed to be affected by some constant source of error, such as would be produced by a mistaken estimate of the position of the comet's center of gravity. He inferred finally that, in spite of previous non-appearances, the two comets represented a single regular denizen of our system, returning once in 37 years along an orbit of such extreme eccentricity that its movement might be described as one of precipitation towards and rapid escape from the sun, rather than of sedate circulation round it. The geometrical test of identity has hitherto been the only one which it was possible to apply to comets, and in the case before us it may fairly be said to have broken down. We may then tentatively, and with much hesitation, try a physical test, though scarcely yet, properly speaking, available. We have seen that the comets of 1843 and 1880 were strikingly alike in general appearance, though the absence of a formed nucleus in the latter, and its inferior brilliancy, detracted from the convincing effect of the resemblance. Nor was it maintained when tried by exact methods of inquiry. M. Brédikhine found that the gigantic ray emitted in 1843 belonged to his type No. 1, that of 1880 to type No. 2. The particles forming one were actuated by a repulsive force 10 times as powerful as those forming the other. It is true that a second noticeable curved tail was seen in Chile, March 1st, and at Madras, March 11th, 1843, and the conjecture was accordingly hazarded that the materials composing on that occasion the principal appendage having become exhausted, those of the secondary one remaining predominant, and reappeared alone in the hydrocarbon train of 1880. But the one known instance in point is against such a supposition. Halley's comet, the only great comet of which the returns have been securely authenticated and carefully observed, has preserved its type unchanged through many successive revolutions. The dilemma presented to astronomers by the Great Southern Comet of 1880 was unexpectedly renewed in the following year. On the 22nd of May, 1881, Mr. John Tebbutt of Windsor, New South Wales, scanning the western sky, discerned a hazy-looking object which he felt sure was a strange one. A marine telescope at once resolved it into two small stars and a comet, the latter of which quickly attracted the keen attention of astronomers. For Dr. Gould, computing its orbit from his first observations at Cordoba, found it to agree so closely with that arrived at by Bessel for the comet of 1807 that he telegraphed to Europe June 1st, announcing the unexpected return of that body. So unexpected that theoretically it was not possible before the year 3346. And Bessel's investigation was one which inspired and eminently deserved confidence. Here, then, once more, the perplexing choice had to be made between a premature and unaccountable reappearance and the admission of a plurality of comets moving nearly in the same path. But in this case, facts proved decisive. Tebbutt's comet passed the sun June 16th at a distance of 68 millions of miles, and became visible in Europe 6 days later. It was, in the opinion of some, the finest object of the kind since 1861. In traversing the constellation Auriga on its debut in these latitudes, it outshone Capella. On June 24th and some subsequent nights, it was unmatched in its brilliancy by any star in the heavens. In the telescope, the two interlacing arcs of light which had adorned the head of Coggia's comet were reproduced, while a curious dorsal spine of strong illumination formed the axis of the tail, which extended in clear skies over an arc of 20 degrees. It belonged to the same type as Donati's great plume, the particles composing it being driven from the sun by a force twice as powerful as that urging them towards it. But the appendage was, for a few nights, and by 2 observers, perceived to be double. Temple, on June 27th, and Lewis Boss at Albany, New York, June 26 and 28, saw a long straight ray corresponding to a far higher rate of emission than the curved train, and shown by Brédikhine to be a member of the so-called hydrogen class. It had vanished by July 1st, but made a temporary reappearance July 22nd. The appendages of this comet were of remarkable transparency. Small stars shone wholly undimmed across the tail, and a very nearly central transit of the head over one of the 7th magnitude on the night of June 29th produced, if any change, an increase of brilliancy in the object of this spontaneous experiment. Dr. Meyer, indeed, at the Geneva Observatory, detected apparent signs of refractive action upon rays thus transmitted, but his observations remain isolated and were presumably illusory. The track pursued by this comet gave peculiar advantages for its observation. Ascending from Auriga through Camelopardus, it stood, July 19th, on a line between the pointers and the pole within 8 degrees of the latter, and thus remained for a lengthened period constantly above the horizon of northern observers. Its brightness, too, was no transient blaze, but had a lasting quality which enabled it to be kept steadily in view during nearly 9 months. Visible to the naked eye until the end of August, the last telescopic observation of it was made February 14, 1882, when its distance from the earth considerably exceeded 300 miles. Under these circumstances, the knowledge acquired of its orbit was of more than usual accuracy, and showed conclusively that the comet was not a simple return of Bessel's, for this would involve a period of 74 years, whereas Tebbutt's comet cannot revisit the sun until after the lapse of 2½ millenniums. Nevertheless, the twin bodies move so nearly in the same path that an original connection of some kind is obvious, and the recent example of Biela readily suggested a conjecture as to what the nature of that connection might have been. The comets of 1807 and 1881 are, then, regarded with much probability as fragments of a primitive, disrupted body, one following in the wake of the other at an interval of 74 years. Imperfect photographs were taken of Donati's comet both in England and America, but Tebbutt's comet was the first to which the process was satisfactorily applied. The difficulties to be overcome were very great. The chemical intensity of cometary light is, to begin with, extraordinarily small. Janssen estimated it at 1/300,000th of moonlight. Hence, if the ordinary process by which lunar photographs are taken had been applied to the comet of 1881, an exposure of at least 3 days would have been required in order to get an impression of the head with about 1/10 part of the tail. But by that time a new method of vastly increased sensitiveness had been rendered available, by which dried gelatin plates were substituted for the wet collodion plates hitherto in use, and this improvement alone reduced the necessary time of exposure to 2 hours. It was brought down to half an hour by Janssen's employment of a reflector specially adapted to give an image illuminated 8 or 10 times as strongly as that produced in the focus of an ordinary telescope. The photographic feebleness of cometary rays was not the only obstacle in the way of success. The proper motion of these bodies is so rapid as to render the usual devices for keeping a heavenly body steadily in view quite inapplicable. The machinery by which the diurnal movement of the sphere is followed must be especially modified to suit each eccentric career. This too was done, and on June 30th, 1881, Janssen secured a perfect photograph of the brilliant object then visible, showing the structure of the tail with beautiful distinctness to a distance of 2½ degrees from the head. An impression to nearly 10 degrees was obtained about the same time by Dr. Henry Draper at New York, with an exposure of 162 minutes. Tebbutt's was also the first comet of which the spectrum was so much as attempted to be chemically recorded. Both Huggins and Draper were successful in this respect, but Huggins was more completely so. The importance of the feat consisted in its throwing open to investigation a part of the spectrum invisible to the eye, and so affording an additional test of cometary constitution. The result was fully to confirm the origin from carbon compounds assigned to the visible rays by disclosing additional bands belonging to the same series in the ultraviolet, as well as to establish unmistakably the presence of a not inconsiderable proportion of reflected solar light by the clear impression of some of the principal Fraunhofer lines. Thus, the polariscope was found to have told the truth, though not the whole truth. The photograph so satisfactorily communicative was taken by Sir William Huggins on the night of June 24th, and on the 29th at Greenwich, the telltale Fraunhofer lines were perceived to interrupt the visible range of the spectrum. This was at first so vividly continuous that the characteristic cometary bands could scarcely be detached from their bright background. But as the nucleus faded towards the end of June, they came out strongly and were more and more clearly seen, both at Greenwich and at Princeton, to agree not with the spectrum of hydrocarbons glowing in a vacuum tube, but with that of the same substances burning in a Bunsen flame. It need not, however, be inferred that cometary materials are really in a state of combustion. This, from all that we know, may be called an impossibility. The additional clue furnished was rather to the manner of their electrical illumination. The spectrum of the tail was, in this comet, found to be not essentially different from that of the head. Professor Wright of Yale College ascertained a large percentage of its light to be polarized in a plane passing through the sun, and hence to be reflected sunlight. A faint continuous spectrum corresponded to this portion of its radiance, but gaseous emissions were also present. At Potsdam, on June 30th, the hydrocarbon bands were indeed traced by Vogel to the very end of the tail, and they were kept in sight by Young at a greater distance from the nucleus than the more equably dispersed light. There seems little doubt that, as in the solar corona, the relative strength of the two orders of spectra is subject to fluctuations. The comet of 1881-3 was thus of signal service to science. It afforded, when compared with the comet of 1807, the first undeniable example of two such bodies travelling so nearly in the same orbit as to leave absolutely no doubt of their existence of a genetic tie between them, and cometary spectroscopy made a notable advance by means of it. Before it was yet out of sight, it was provided with a successor. End of Part 2, Chapter 11, Part 1. Recording by Aaron Carlo in San Clemente, California.